خلاص we start.
Yeah, we can start.
Yeah. Hola. Okay. Not a big audience, so that's nice. Nice. Okay. So, morning, and today we will speak about the geometry of, optimality. And it will be a fairest part because I hope to do a few of these. And because it's a fairest part, it will be about basics and LBs, linear programs. So, okay. I will just say the objective of this session, which I hope will be very short, but it will be nice. The objective is to go from simple observations to generalizations about some structural properties of some objects, and then also appreciate that these structural properties are not just like intellectual curiosities, no? They lead to some computational algorithms, so they make sense. Okay. And these objects will be like a couple of sets that we will discuss. So, and of course, we will start with an example so that everything is concrete, everything is with numbers. Okay. But to do this, I will fix a notation. The only notation that I will use is the inner product. So if I have two vectors in Rn, their inner product, I will write it as this. And this is simply x transpose y. So the vector product, right? So that's the only notation that we will use. Of course, you know that this is linear in y and x, so it doesn't matter. Okay, and we will start with an example because examples are nice. So example for a linear program. You are asked to solve a linear program. You are asked to minimize a linear function, obviously. Our optimization variable is x. C is constant, is a constant vector, such that you have, I will just stick to inequality constraints to make everything simple. I have a set of inequality constraints, 5 inequality constraints, defined by some vectors ai less than or equal to bi. This means that, of course, this means that ai transpose x less than or equal to bi, right? From the, and I is from 1 to 5. So 5 constraints of this type. Okay, and let's make it concrete. So let's give some numbers to ai and c, because these are constant. So I will assume, just to be able to draw everything, that x is a vector in R2. So just two components. Let's give ci minus 1, minus 2, transpose, of course, because it's a vector. So minus 1, minus 2. Let's start with A1, I don't know, 1, 0, corresponding to which B1. So this means that X1 less than or equal to some value. So B1 less, I don't know, 3, A2, 0, 1, transpose, B2, 3, the same. And then I can draw also at the same time so that you appreciate this. X1, X2.
I have a question.
Yes.
Why we adopted the notation?
Because it will make things easier, you will see, in the computation. Yes.
And do we have some name for the notation?
It's the inner product. It's the inner vector product. It's a standard notation. So there is two products that you can define in a, so yeah. So, okay, A1 is a vector 1, 0, right? So 1, 0, like x1. It selects only the components x1. And it says that x1 is larger than or equal to 3. So this vector, so 1, 0 is a vector of this type, right? So from 0 to should be orthogonal to x1 should be 3 or less. So it's orthogonal to this plane. Everything below is, yes. Everything below should satisfy this constraint, or everything in this. The same for A2. So it's a vector 0, 1, and everything here 3. So we selected all of this region by these two constraints, right? Is it? Yes. Now let's add a few constraints to make it nicer. So A3, let's select the positive x1. So minus 1, 0, B3 equals 0. What does it say? That x1 minus x1 less than or equal to 0, which is x1 larger than or equal to 0. So we select everything, above, so everything positive x1. So here we look at minus 1, 0, and this, everything from this side is selected. I can draw it with the red. I can draw this with the red. So now we are in this lab, right? And let's do the same for x2, 0 minus 1, b4 equals 0. That means I select the positive. That means this vector is 0 minus 1. So now I have this square. Well, let's make it not square because it's so we add just one constraint. So x1, so these are all transpose. x1 plus x2 less than or equal to some value, let's say 4. To understand how this looks, so this is a line, right? So this corresponds to x1 plus x2 less than or equal to 4. Let's fix it. So let's take the active constraint. So x1 plus x2 equals to 4. This is a line. So if x1 is 0, then x2 is 4, right? If x2 is 0, then x1 is 4. So I look at the points 4, 0 and 0, 4, and I draw a line that passes through these 2 points. So this should look like this. So now our constraint set, this is the region that satisfies all the constraints, right?
The group only?
No, region, yes. A region that satisfies all the constraints, all the 5 constraints. Does it make sense? Okay. Now we make some observations. Okay. So my cost function is C, the inner product C x1, which is minus 1 x1, so minus x1, minus 2 x2. This is my cost function that I want to minimize, right? So this corresponds to minus x1 minus 2 x2. And I want to minimize this function such that the point that is minimizing this should lie inside this region. This is my problem. Okay, how to solve this? Okay, let's say that, from intuition, we understand that this cost function should be at the minimizer constant. Should be some constant value, right? Should be some constant, but minus infinity, minus 200, minus whatever. This is the optimal value. And I want to look for this optimal value. So suppose that this is equal to C, some constant, C here, so it's a bit alpha, right? It's a constant value. Now, the set, and this is a definition. This set, I call it L alpha, you can call it whatever, where the cost function takes a constant value alpha is called a level set. Level set, because the cost function is constant, so it's level. It's constant at this value, right? Fortunately for our problem, because it's a linear program, this thing is an equation of a line in R2, right? This is an equation of a line. So if I change alpha, decrease it, I should always draw lines that should touch this region at some point. That's the idea. So, okay. And this line is always perpendicular to C because of how we construct it. So C is minus 1, minus 2, this vector here. So this line will have this shape, like lines depending on alpha. Let's select a couple. So suppose alpha equals minus 3, so minus some value. Minus 3, that means minus x1 minus 2x2 should be equals to minus 3. So if x1, I don't know, is what? Is 0, I don't know, somewhere here in this line, then x2 should be 1.5 minus 2x minus 2, 1.5 equals minus 3, right? So 0 minus 1.5. So this is this point, suppose. Then if x2 is 0, then this should be minus 3. So this is a line that looks like this. Should always be, so I don't draw correctly, but should be perpendicular to this C. Yeah, exactly. C is the slope. So if I select alpha minus 7, magic, this is the last point that this line touches this polytopic. It will touch it here. So if I continue decreasing the level sets, the value of alpha, the last time I touch this feasible set is the optimizer, is the best solution, right? Is the minimum value of the cost function. And the point x corresponding to that minimum value is the solution for this. Does it make sense? Okay, so we move the line until it touches the last point. Somehow it touched this set at this point, which is particular point. It didn't pass through some point inside and then disappear and appear somewhere else. It touched it at a vertex of this, right?
But you might touch
at a line.
The optimal point, right?
Yeah?
That's not the optimal point.
This is the optimal point.
That's the optimal point?
Yes.
Okay.
Yes. Because imagine that you have a level set and you keep decreasing the cost function along this level set, along the slope of this,
Yeah.
and you are passing this line through the feasible set. At some point, it will touch here. Or here, of course.
Yeah.
Yeah. But
One more point at the edge.
where? Here?
The bottom one.
Yeah.
Here? No, because of the slope of C, the time it touches this will be before the time it touches this.
Okay, just imagine
If C was
slope
different,
is such that it touches both the point.
yeah, you can find non-unique solutions. I'm not saying that it's a unique solution. But in this particular example, because of the slope, we will touch here. Okay? Okay.
But it's like, it shouldn't be that what's the first vertex you touch, right? Because
No, not the first vertex. The last vertex you touch in the opposite direction of C.
yeah, like the opposite direction of the grid.
Yes, exactly.
Yes.
So we want to maximize the objective or minimize the objective?
Minimize the objective is minimum of C, the inner product Cx. So here, the first time here, it was minus 3. Then I keep decreasing until I reach minus 7, which arrived at this. If I put alpha minus 8, or minus 9 to make it easier,
Okay, no, I see.
and you substitute, yeah, exactly. You will see that this line is here, which is outside. Okay, so the observation is among the possible solutions in the feasible set, we touch the vertex, which is a particular point. It's not any random point. So maybe this is this always the case? Like, are we always finding the optimal in a vertex? That's the question, right? Because if we are always finding the optimal at a vertex, the problem would be to just find all the vertices and evaluate the cost function. Yeah. Okay, so let's answer this question. So this is
So I have like a follow-up question.
yes.
Okay. If suppose we found the two vertices that is touching the slope. Okay. So depending on like we want to maximize the function, okay? So out of that two will be providing the one will be providing the maximum, correct?
No, because,
So
okay,
we have two possible solutions.
if you have two possible solutions, by definition, the cost function would have the same value at the 2 points.
Okay.
So this is a non-unique solution situation.
Okay.
So you can pick any, right?
Pick any, okay.
Yes. So let's try to, I mean, from this observation, make some intuition and then arrive at an algorithm to solve these kind of problems, right? Or follow the steps of Danzig in the 30s, back in the 30s.
But just to come back to the bigger picture,
Yes.
we are minimizing. Let's speak, geometrically.
Yes.
We are minimizing the dot product. We are finding the vector that minimizes the dot product, right?
We are finding a point
A point.
that minimizes a linear function, which is a product, a vector product.
Which is what
between
we
two.
invented, yeah.
Yeah. But this point that minimizes this vector product has to lie within a feasible set. And the feasible set in this particular case is, okay, definition, because it's important. Okay.
Yeah, the reason I'm saying is that, a point can be also a vector, right?
Yeah,
We
you
can say that-
can think about it as a vector or a point. Is the same, yes.
Right.
Yeah, that's
Okay.
correct. That's correct. So in this case, it would be this vector, which 1, 3. Why we will see later, because it's obvious,
Right.
right? Okay. So let's define first a couple of things. What is this feasible set, and what is interesting about these vertices about the feasible set? So the feasible set here, in this case, is called a polytop, which is simply the convex combination of these vertices. In other words, is the intersection of the constraints, right? This is what we did. We draw all the constraints and we found the intersection point. So P is equal to the intersection, I equals 1 to 5. It was AI x equals, no, less than or equal to BI. This intersection, these are the 5 constraints, right? I equals 1 to 5. If I put this as rows of a matrix, the matrix, call it A, then this would be AX less than or equal to B. I stack the BI's on top of each other. So whenever you see this, it's either a polyhedra or a polytop. Polytop, because it's closed, it's bounded, it's compact. Polyhedra can be open, right? Could be open on one side. But in our case, because we want simple, polytop, right? Closed. So closed means what? Means it has finite many vertices, right? Okay, so let's define what these vertices are and talk about their properties. So a point, any point in this P, X call it, that is part of P, that is within P, is called an extreme point or a vertex, depending on the author, extreme point. Okay? If it cannot, and here is important, cannot be written as a convex combination of points inside. And I will, cannot be written as x, for example, half y plus d, like the average of 2 points, where y and z are inside B.
Now, I have a
So,
question.
yeah.
Sorry to interrupt. When you say the extreme, meaning for me, I get the idea that we are looking a point on the edges
Yes.
of the polytop.
Yes.
Okay.
Yes.
Okay. Sorry.
So this definition defines vertices or edge points.
Okay.
So points that cannot be written as the midpoint between 2 points that are both inside. So if I look at this, you cannot find 2 points that are both inside for which this is the middle point. If you select this point and this point, this is the middle point of them, but one of them is outside, right? If you try to do this and this, the middle point of them is here. So
Okay.
it cannot be written as the midpoint of 2 points that are inside.
It's just a rigorous way to write the vertex definition.
Yes.
Right.
Yes. There is another way, and we will use both ways to write proofs. That's the main idea. Or equivalently to this, a more difficult way is cannot be written as convex combination of vertices of P, other vertices of B. This is a circular definition, which means what? Pick some lambda, some parameter that is between 0 and 1, less than 0 and larger than 1. So x is never equal to the sum of, well, you cannot write it as sum of, maybe it's better to just pick 2, lambda v1 plus 1 minus lambda v2. It's the same. Just here we replaced in this lambda with half, right? And here v1 and v2 are vertices, not any points. But it's the same definition. But the definition is clear, right? Does it make sense? It's clear? Okay, how to find these vertices? Because this is the...
I just have a doubt. When
Yes.
you say the convex combination, so it means I didn't get the meaning properly.
Okay, so now I can do something here. So by definition, a convex combination of 2 points is, so suppose I have x1 and x2. These are 2 points in general. Their convex combination is lambda x1 plus 1 minus lambda x2, provided lambda is positive, so it's larger than 0 and less than 1. This defines, if this is a point and this is a point, it defines the segment, the line segment between these 2 points.
دكتور بس الكلام مش مبين maybe you can-
Yes.
more pressure on it.
Yes. So this is my point x that I want to specify as a convex combination of 2 points. This is x1, x2, right? Depending on lambda, this x could be here, 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 or if it's lambda is half, is in the middle.
Oh, okay.
So these are called convex combination, and they are used to define convex sets, which I mean sets for which any convex combination between 2 points always is inside the set. So if you draw a line inside the set, every
Thing is in this.
every point of that line is inside.
Yeah.
So this is a convex set. This is not a convex set because you can find this line that goes outside.
For me, when I saw this definition, so I thought the lambda is like a binary variable.
No, is
It takes value in between 0 and 1.
yeah, it's just a parameter.
Yeah,
Yes.
parameter.
It's a fixed
Okay.
parameter. Okay. And I mean, okay, we can be rigorous. So let's step back. Our question is, okay, we had a linear program. We wanted to minimize a linear function subject to the minimizer should lie in this set. And we found that if we move the level sets, we will reach a minimizer that is on the vertex. Now we define the vertex. We want to know how to compute this vertex, how to know the coordinates of this vertex, right? Because now, okay, we have a definition of a vertex, but this one does not allow us to compute the vertices of P. So let's try to compute.
So our final goal right now, what we are answering is, do we always find optimality at the vertices?
As the vertices for a
Okay.
linear program, yes. Yes. So here I can do, and I hope this is, maybe, okay, so, so let's define something called a calligraphic, because I want it to be different from that A. So A with this shape, right, of X. So this A is associated with a point. Is the matrix composed of rows AI in which the constraint at this point is held with equality, not less than or equal to, but with equality. That means this is called the active set, right? Active set is actually the set of indices, but we replace it with the matrix. So, example, here at this vertex there is two active constraints, this constraint and this constraint, right? And this constraint is defined by 0, -1, and this constraint is defined by 1, 0. And BI's corresponding is 0, 0. So larger than x1 is positive, y1 is, and x2 is positive. Actually 0, 1, 1, 0. So this A matrix here is actually the opposite of the identity, sorry. 1, 0. This A matrix here. Does this make sense? Okay.
So the A matrix is giving you the first quadrant. Okay.
For this point, yes. Yeah, exactly. It's giving me the first quadrant, yes.
Right.
Okay, because these two constraints that tell me x1 is positive and x2 is positive is the definition of the first quadrant, right?
Yeah.
Yes. So we define this. So the claim is this point, is an extreme point okay, if and only if the rank of this matrix, rank of A of X, is equal to n. In our case, n is 2, the dimension of the space, which is 2, right? Because we are living in two dimension. Yes. So that means whenever I am at a vertex, the number of constraints that are active on the vertex is either at least equal to the number of the dimension of the space, could be more, but the matrix that I construct should have that rank. For example, if I look at here, every constraint has at least 2 active constraints. Every vertex, right, is defined by at least 2 constraints, 2 lines intersecting. I mean, okay, okay. Of course, okay. To prove, to prove something like this. Yes.
So the definition of AX can be varied, like the size of the matrix can be varied depending on
the active
point
constraints.
The active sets. So
Yes.
like, yeah, and
So,
also like if the X is like, for example, if we just consider a point X inside of the region.
Yes. Then this matrix will be empty.
Empty.
Yes.
Okay.
Yes. Exactly. And the null space, in fact, of the matrix will be of
So
dimension.
because of the condition of if and only if, so like vertices should be at least, it also mentioned like it should be, the extreme point should be somewhere that has at least like 2.
At least some active constraints
Active
that are 2.
constraints,
Yes.
yeah.
In this case. Yes.
In this case. Okay.
And that's why we write not A, but A of X, because it depends on the point at which you evaluate the matrix. Yes. Okay. So, okay. Let's start. So the idea is that I am saying, if the rank is 2, the point I am evaluating the matrix at it is extreme point. If the point I am evaluating the matrix at is extreme point, then the rank is 2. This is if and only if, so 2 directions, right? Whenever you see if and only if, you need to prove in 2 directions. So let's prove the first direction, and then we're done. We skip the second direction because so the proof for this, okay. And this technique is standard. Huh? So I assume I start with rank of A of X equals to n, and I want to show that this X is extreme. I have the matrix full rank. I want to show that this is extreme. Suppose, so directly you use contradiction because this is the usual. So suppose X is not an extreme. So, because if I show that this is a contradiction, that means X is an extreme, and so I prove this. So, okay, suppose it's not an extreme, but the constraints are active on it. If it's not an extreme, by the definition, I can find these 2 points, right, that are both inside P, and I can write x as half y plus z. So that means x is equal to half y plus z. Y and z are in P. But since y and z are in P, they should satisfy all the constraints, active or inactive. That means ai y less than or equal to bi, ai z less than or equal to bi. Right? Okay. But at this point x, we know that the constraints are active. These constraints are active. Or no, you can write ai x, which is equal to, in this case, replace x by half y plus z. ai half y plus z, which, because this is linear, I can put the half outside, ai y plus half ai z, right? Yeah. But okay, I selected ai to be in the one of the rows of this matrix. So that means this part should be equal to bi, should be active, right? Does it make sense? Okay. Okay, so if I multiply 2 to get rid, then that means the sum should be equal to 2bi, right? Okay. So these are 2 numbers that are both less than or equal to bi, and their sum is 2bi. That means that 2 numbers are bi, right? There is no other way. Yes. If I have 2 numbers that sum to 2bi, but they are both less than or equal to bi, so this is equal to this is equal to the, so the constraint ai is also active at these 2 points. Okay, so now I know that ai y is equal to bi, ai z is equal to bi. Okay, if I subtract this, then ai y minus z is equal to 0, right? In matrix form, this is this matrix multiplying a vector y minus z is equal to 0, right? But I know that this matrix is full rank by the assumption here from the direction. So I started by assuming that the matrix of the active constraints are full rank, and I wanted to show that the point at which it is evaluated is an extreme point. So I started by this assumption. So this assumption holds here. If that assumption holds here, then the only solution to a linear system like this, in which the matrix is full rank, is this to be 0, right? Because there is no null space. So that means y minus z is equal to 0, which means y equals to z, right? But if y is equal to z, and I plug it here, that means y equals to z equals to x. So which is a contradiction, because these are not 2 points in B that are separate from x. That means I cannot write x as a convex combination of 2 points other than x, which means that x is an extreme point, right? So this closes this direction. Is it, does it make sense?
It makes sense.
Yes, yes.
And what do you mean by extreme point?
Okay, so.
Not, I get like mathematics, but.
No, yes, yes. So in this shape, the extreme point is a point that cannot wiggle inside the polytope, is on the edge, is protruding from the polytope. So it's the vertex. Like this point or a point in this line could not be an extreme because there is neighborhood points of it that are inside. But this is protruding, it's outside, it cannot be written as a convex combination of 2. Right? Is it? Yeah. So the corner, basically, is the corner of the shape. So in a square, the corners are the extreme points. So if you have a square,
Even the edge points in the edge will be extremes?
no.
No.
Yeah. Well, I mean, no. Because from the definition now, we can go to the mathematics. If you pick a point here, this point, in the edge, right? You can find 2 points on the edge that belong to the square, for which this is the midpoint that can be written as half of. Does it make sense? Okay. So yeah, extreme points in this case are just corners. So, okay. So now we know how to compute the vertices. This exercise is not important. Important is this statement. The statement says, okay, I have the polytope written as this, right? And this A is of dimension m by n. M is the number of constraints. Okay. Now, any point that is extreme I should select n rows in that are full rank and solve a linear system. Right? Does this make sense? So I have this matrix, for example, in our case, in our example, it was the fairest constraint was 1, 0, 0, 1, minus 1, 0, 0, minus 1, and then 1, 1, right? So whenever I want to find a vertex of this shape, I take a 2 by 2 submatrix, for example, the fairest 2. I say x, and this was corresponding to the constraint that 0, 0. I think B1 was 0, 0, and then 3, 3, no, minus 3 or 3, 3. Yeah, because x is less than 3x, and 4. So this was the vector B. So I take this full, so I say 1, 0, 0, identity multiplying x equals 0. The solution to this is this point, because it's a 0, 0. If you replace, you take this. So 0, so x2 equals 0 for sure, and then x minus x1 equals 3. Right? And then you take this. That means this minus 3, this minus 3. Right? So 0 and 3. Or
So
3 and 0.
you start taking
Submatrices of dimension.
submatrices that are 2 by 2.
Yes, that are 2 by 2 or n by n in any n.
To start scanning for these vertices.
Yes, so we will come to why we do this. Okay, so this is how we compute the vertices, right? And we scan the vertices in this way.
And you would get all the vertices this way, right?
Yes, and question for you. How many vertices when you have m constraints for n is m choose n, right? Is the combinatorics, is m choose n. This is a factorial. At most, it's not necessarily equals to this, but at most there is factorial m, factorial n, factorial m minus n. Right? Is the combination.
Is the A matrix always like full rank?
The active constraint at a vertex,
Yes.
yes. The active constraint at a vertex, yes.
So we can use
This A
the,
matrix is different from this,
yeah,
right?
yeah. So like we can use the inverse, like it will be the
Exactly. So
submatrix.
exactly. So
and we
you
can
take
use
this
the
linear system inverse.
so
That's
that
it.
we can easily compute them.
Yes,
Okay.
exactly. It's a linear system with a full rank matrix. You can use not even pseudo inverse, it's inverse, and that's it. Yes.
To find all the points at once.
Not all the point at once. You can find one by one. This A matrix is associated with the point X.
So we can take the submatrix
Yeah, the
each
submatrix.
time and
Take
then
this,
take
this will
the
correspond to one
inverse
point.
of the submatrix.
And you choose from this 5 by 2,
Oh, yeah.
like different combinations of 2 rows. Like these two, these two, these two, then these two, then these.
So it's not just submatrix.
Yeah,
it's the
it's-
combination.
And this is called the brute force, and this is the simplex algorithm, which you, okay. We'll come to it shortly. So, okay. So now, let's go back to the question. We're discussing the geometry of optimality in linear programs. We said that, okay, the question is, from the feasible set, which has vertices that are geometric objects, and the level set, which is a geometric object, the way they interact tell us where the minimizer is, and then we ask the question, Is the minimizer always at a vertex, at an extreme point? Okay. Well, now with all of this, we can prove this, this statement, okay? And this is the last computation and math thing, believe me. I know it could be a bit sometimes. But I hope that you appreciate the fact that you can make the observation, very simple observation, and then you can actually prove it. You can actually. So, okay. So we answer our question. Theorem. Typically, this you will find it in textbooks as the fundamental theorems of linear programming, which says if x star is a solution, to our LP, then it is attained at a vertex, at an extreme point, right? So whenever, here we are not talking about like, actually, x star is a solution to if it's attained at, is attained directly, because this should be very, x star is a solution to a linear program, is always attained at a vertex. Because if I say if and only if, then that means there is no solution apart from this. No, we are not talking about uniqueness. We are talking about even if there is multiple solutions of the linear program, at least one of them will be in a vertex. At least one of them will be in a vertex. Okay. And then, okay, should we do this or, it, you can be, okay, homework. It's the same. It's the same machinery. We'll use the definition. We'll assume contradiction. We'll try to find it. Actually, let me just give you the sketch. Okay, so the sketch is the following. Suppose alpha star C x star. What does this mean? This means that this is the optimal value of the cost function and is attained at x star, right? Because this is our cost function, right? So you want to show that, and suppose also, always contradiction, x star is not an extreme point. That means it could be written as the convex combination, lambda, of two vertices. The second part of the proof, lambda v1 plus 1 minus lambda v2, right? This could be written like this. The idea is to show that the cost function at v1 and at v2 should be equal to x star. That means v1 or v2, one of them at least, will be a solution as well, which means, but these are vertices. And then you close. But okay. Show at least one of v1, v2 is such that CVI equals to alpha star. And this you can do, the computation. Okay. So this is our question. We started with this question. There is a geometric fact that is nice. We could intuitively think about it by just moving the cost function and see where it's minimum. Yes.
Yeah. So when you say that show at least one of v1, okay.
Yes.
So at that time, the lambda will behave like a binary.
It's a number. It's a real number.
Yeah. So it takes 0 or 1.
No. It's between 0 and 1. It's
but to prove this thing, okay, to show that at least one of the v1 or v2.
Okay, so let's do it.
Okay.
Let's do it because it's quick. So we know this, right? Yeah. And then we assume, we say that it's a vertex, but now for the proof, we assume it's not a vertex. So we write it as this. Yeah. Now let's substitute this here. So alpha star should be equal to C lambda v1 plus 1 minus lambda v2. Okay? is equal to C lambda V1 plus 1 minus lambda. You can take this out because it's a real number. C V2. Right? Now, but these are so but C V1 should be less than or no larger than because we assume that X star is the optimal. So the corresponding value is the minimum value. So any value anywhere else should be larger than or equal to this value, right? So alpha star, right? And so for this, larger than or equal to alpha star. So you notice that these are two numbers, these inner products, that are larger than alpha star, but their average, their weighted average, is equal to alpha star. That means what? This equals to this equals to alpha star.
Okay.
Which means this vertex attains the optimal value, which is a contradiction. That's it. Okay. That's why I said it's a homework, because it's simple. It's the same machinery. Just here we use the constraints to do this manipulation. Here we use the cost function to do the same manipulation, basically. Okay. So we come to the fun part, maybe for engineers. For us, I mean, this was fun, I think. And we conclude, so at some point, I don't know which date, 1930 something, there was a guy named George Danzig. Okay? And probably Danzig, probably you hear this name.
Stanford.
Huh?
Right? Or
Yeah.
MIT.
Yes, Stanford. And this guy made the same observation, the same proofs, the same things. Okay, for any linear program over a polytopic constraints, just by moving the level set, I attain the minimum at a vertex. Is it possible to generalize? Yes, and you write the proof, and it's quite simple, a two-line proof. Then that means the problem reduces to finding the vertices and see which one is better by evaluating the cost function at these vertices. So, wrote Simplex, which is still, still the way we solve with modification. We solve linear programs. So, and it's just a three-step algorithm, right? Find initial vertex x0. How to do this? This theorem, this lemma that we proved. Take n by n combinations of rows, solve a linear program, you get x0, right? Okay. 2, this is the most intriguing. Find neighbors. How to do neighbors of x0. Call it, for example, x1, or several of them at the same time, and evaluate the cost function, like C x0, is it larger than or equal to C x1? Which one is better? Which one improves the cost? So you don't need even to compute anything. You just evaluate, function evaluations. Evaluate here and evaluate here. If this is better, keep the active set matrix, which is A of x1, drop the constraint corresponding to this, and go to the next neighbor. Repeat until no improvement. So for this, we take this first submatrix, 1, 0, 0, 1, x equals 0, 0. We found this this vertex. This is our x0. What is the cost function at this C x0 in this case is equal to C, the inner product with 0, which is equal to 0, right? So this is the cost function now. Find the neighbor. Find the neighbor means drop one constraint and add one constraint. For example, we drop this, and we add this. No, this one, for example, because it makes us easier. That means our matrix now is 1, 0, 0, minus 1, x equal to 0, minus 3. Right? We solve it, we find this vertex. So we go here. What is the cost function here? This is a 0, 3, right? So c x1 is equal to minus, so c was for your minus 1, minus 2, right? So minus 1, 0, minus 2 equals to minus 6. So this is improved. So I drop this, I keep the active constraint, the active matrix, so this matrix here, then drop this, add the constraint to this, add the last constraint, 1, 1. Then I will go to this vertex and I will stop. So this is called pivoting. You say a simplex pivot. And this is called, the whole thing is called the simplex walk. And this is a brute force simplex. Huh? There is some improvements here and there. People came up with better ways to because this is not guaranteed to not visit all the vertices. Because you could visit all the vertices until you reach the optima. Some people don't like that. They want to visit as fewer vertices as possible. So there is a few tricks to modify. There is still open problem that is no polynomial time worst case. There is no still proof worst case that there exists a modification of this algorithm such that you solve in polynomial time. So you don't visit all the vertices, right? But this is a big open problem in computer science. I don't know.
So it is actually the method of reducing the subsystems.
Yeah, it's a standard method to solve linear programs everywhere. Like any solver that you open, it's a variation of this for linear programs. I mean. If you look at the code, it's just these 3 steps.
This is applied in which field? Because I studied this, but I forgot in which subject.
But this is linear programming, is mathematical optimization.
So, implementation, you studied this in some application World War II.
Yeah, but Danzig actually, the 30s. So he did it in the middle of, yes. It's always, linear programs could be used to cryptography, to do a lot of things. Guidance of missiles, I want to hit a specific region.
Well, if your problem reduces to a linear program, you're lucky.
Yes. In general, I mean, yes. Some people find ways to ram a linear program in their complicated problem. Right?
Yeah.
Yes, yes. So it's, but, okay, so I said this is the geometry of optimality part 1. So this is the basics, LPs. There is similar observations that you can make about more general like quadratic programs. Quadratic programs that are quadratically constrained, etc. For which you start with a simple example, you make an observation. It will be different than this. It's not a vertex, but something else. And then you can make simple proofs and arrive at an algorithm. For example, an active set algorithm. And I hope this was useful.
Yeah, very useful.
It's clear? Yeah. If you have any other questions.
No?
Buonissimo.
Recherche opérationnelle.
Yeah.
For recherche opérationnelle.
I have like one question, like maybe it's not that.
Yes.
Maybe it's
No, no.
okay. Okay, here we have like 5. Let me add one more. Like
Yeah,
6.
yes.
Okay.